because I'm sure that once you go ahead and start reading papers on petrographic string theory, you will encounter it, so it would be useful. And then, so that's a plan for today's lecture, maybe a little bit next one. And after that, we have to think what we're going to do for the last lecture. So I think there will be 3 more lectures. So today, then we continue slightly discussing the scattering amplitudes, study strings in curved space-time. Okay? And then I want to go back into this idea of gauge fixing, right? So we did all the computation. We will be doing computations in conformal gauge, and you've heard a lot about modular in string theory, right? And so I want to talk a bit about that, and I'm going to show on some simple examples how modular show up, and they show up in a very interesting way. So they show up as a failure to do complete gauge fixing. Because there are some mismatch about freedom you have in fixing parameters by doing reparameterization and wild transformation on wall sheet and going to a particular gauge. So that's where the modular will come from. So that's what I want to explain. And after that, we go and we study the simplest scattering amplitude. Right, so the S matrix element in the string theory on a sphere, and we should be able to derive Veneziano amplitude. Okay, so that's roughly what I hope I will finish the course with. And if I have more time, then we will go and we will study T-duality. Okay, so I think, and then, well, it's unlikely we will get to a D-brane, but at least, you know, that's the beginning that you need to do in order to start discussing the D-brane physics. All right, good. So what we, let me just connect to last lecture. So we studied scattering amplitudes. And so the reason, so we discussed that the only scattering amplitudes we can study, so those are the scattering amplitudes in which we scatter states, right? And we prepare those states at minus and plus infinity. So this is t equals plus infinity, this is t equals minus infinity. Those are infinite cylinders attached to some region inside, in which we have scattering of the strings. And so this picture, the picture of strings coming in the middle here and scattering. So this picture was in the omega coordinate, and so when we go to the z coordinate, then the picture becomes, in this particular case, so this becomes just a sphere, right, in that coordinate, with insertions of local operators corresponding to the string states. And so then what we did, we kind of wrote a general formula what the S matrix for scattering would look like. So we were assuming that we scatter a state GI here, which have a momentum KI. And so we wrote the expression, what does the S matrix element looks like. So I have a scattering amplitude J1, and then I have up to N. So I can consider that I have N infinitely long cylinders attached. So each of them comes with its own momentum. And so in order to evaluate this, we have to evaluate the following passing integral. So we have to, so this is in a closed string, right? So this is rolling closed strings. Okay. So we have to sum over compact topologies of wall sheet. So this is an example where the leading order scattering, where I insert local operators on the sphere, and so there is a high order correction to this process. High order correction. And so the high order correction will show up when I consider topology of the torus. That's topology of the wall sheet, and I insert exactly the same operators on the torus. So that's where the sum over all topologies come from. And then we have a path integral, right? So dx dg. So I'm not writing it in a ridge fixed method. And we'll discuss, as I was promising you, we'll discuss in more details the subtle bits involving the ridge fixing here. And so you just e to the minus s, right? So I have ss minus lambda chi, and then what is happening after we map this infinitely long cylinders, we get local operators, and so in order to get answers which are diffeomorphism invariant from the perspective of bullshit, we have to integrate over the bullshit over the position where we insert it. So g of sigma I. And I have corresponding vertex operators at ki inserted at sigma. Okay? And so this is a product of all insertions from one to n. And so this compact over sum over compact topologies simply means summation over surfaces of different Euler characters. And so the ones that we discussed before were oriented surfaces, right? So we talked about the sphere, and we talked about homogeneous curves. Right? And so the way how you think about homogeneous curves, what you do is you take a sphere and you attach handles to it. And so what I want to do now, I want to talk a little bit about unoriented surfaces. And the reason I want to talk about this, because in general, this Euler character is 2 minus 2g minus b minus c, where g is the genus of a surface, how many handles you have, right? So this is number of handles, and so this guy is number of boundary components. And so this C, something that I want to talk about now, is what's known as a cross-cap. So this is number of cross-caps. So those cross-caps, they arise when we talk about unoriented surfaces. Okay? So let's go ahead and talk about that. And so I will discuss kind of the simplest unoriented surfaces. So they will, so those will be the one without boundary, relevant to closed string. So the first unoriented surface that will arise in closed string is a Klein-Bottle. I will talk about Klein-Bottle. Okay. So this unoriented surfaces arises in closed strings. So relevant for unoriented closed strings. And another kind of the first unoriented surface you discover you have to deal with when you talk about open strings is here this string. Okay. And so this is relevant for open unoriented. Okay, and so if you wish, what I'm going to talk about, I'm just going to explain how you think about this. Okay. So remember that when we talk about our unoriented strings, we have an additional symmetry in unoriented strings. In the case of closed strings, closed unoriented strings. So what we have a symmetry where one of the worldsheet coordinates sigma 1 goes to minus sigma 1, and open unoriented strings. So what's going on there? So in this case, sigma 1 is identified with 2 pi L, right? And so in the case of unoriented open strings, so sigma 1 is an interval, and so the way how we set up unoriented strings here is by saying that there is a symmetry that sigma 1 goes to 2 pi L minus sigma 1. Okay. So the point is that that kind of identification is a Z2. So Z2 is a type of identification that you are doing, so Z2. So it's a natural that all these unoriented surfaces, Klein-Bottle and Möbius strip, can be represented as a Z2 orbifold. Right? So what we're going to talk about that we'll talk about Klein-Bottle, Bottle, and Möbius strip as some particular Z2 orbifold. So some kind of an identification, Z2 identification of Saturn oriented surfaces. And so oriented surfaces here will be a torus. So that's relevant in this case, or a cylinder, which will be relevant in Möbius strip. So we'll try to see how we can get these unoriented surfaces by taking something that we are familiar with and making an orbifold, making some Z2 identification. So, so let me start. And so I'm going to discuss first the Klein-Bottle. Okay. We'll talk about Klein-Bottle. So here I have sigma 1 and sigma 2. So let me just introduce some conventions that I'm going to be using. Right, so sigma 2 is periodic. Okay, so let me just go slow. Okay. So I'm just going to write down my surfaces with identification. So let me explain how I'm doing this. So this is 0, this is 2 pi, and so this is 2 pi L. Okay, so I have a region here, and what I'm saying that this is the way how I represent the cylinder. So this is my cylinder, and so what I'm doing an identification, which is sigma 2 is identified sigma 2 plus 2 pi. So the arrows here means that I have to glue a side with a directed arrow in an appropriate direction with another side which has the same type of arrows. Right? So is it clear? It's really like I'm cutting the surface and laying it flat. Right? So that's the way how I'm thinking about a cylinder. And so now it becomes obvious how do I think about the torus, right? So it's just easier to think about orbifolds that we're going to discuss in this language, right? So when you cut out the surface and spread it flat on the table. So this guy is a cylinder, and so I can think about the torus now in the same way. So I'm always gonna assume that sigma 1 goes from 0 to 2 pi L and sigma 2 goes to 2 pi. So you have 0 to 2 pi L, and this is 2 pi. And so in order for me to get a torus, right, so first I have to make a cylinder. So I make a cylinder by gluing those two sides. And then once I have a cylinder, okay, so that's my first gluing. So in order to get the torus, I just glue this circle up here to here, which means that I have to make an identification of those sides. So this is a representation of the torus, right? And so this is torus. And so here, what I'm doing, well, first, I build up my cylinder, which meant that I identified sigma 2 plus 2 pi. And second, I have to identify the vertical lines, which means that I identify sigma 1 with sigma 1 plus 2 pi L. Okay? So is it clear so far? A cylinder and a torus. So in this language, I'm going to define what I mean by a Klein bottle. Okay? So a Klein bottle is a Z2 orbifold. What is an orbifold? An orbifold means that I identify 2 points. Okay, so the easiest thing to think of is I go what's called a double cover, and then on that double cover, I say that 2 points are identical. Okay? So what is also clear is that since I go on a double cover, what I did, I increased the volume, or in this case, the area of the surface by a factor of 2. Okay, so so it's natural then to talk about this action, Z2 action that will produce unoriented surfaces on its double cover. Okay, so I'm just going to go on a double cover, and double cover simply means that I have to make, if you wish, my fundamental region here. Okay, in sigma 1, sigma 2 plane, twice as large. Okay, so let's go. So we do go on double cover. And the reason is that after we do a Z2 action, we will go back to our standard string length. Okay, so we go on a double cover, on this double cover, what we're going to do, we're going to do the following identification. So sigma 1 goes to sigma 1 plus 4 pi L. Okay, so what I did here, I simply increased the fundamental region by a factor of 2, right? And sigma 2 stays the same, plus 2 pi. Okay, so this is a double cover. I increased it by a factor of 2. So then, in order to get a Klein bottle, I have to specify additional identifications. How do I identify points on this larger torus, right? So I have now a torus twice as large. So this length is 2 pi. This length is 4 pi L, right? In order for me to get that Klein bottle, I have to identify some points. And the identification is done in the following way. 4 pi L minus sigma 1 and sigma 2 plus pi. Okay, you can verify that if you add twice with this, you will go back to sigma 1, sigma 2. Okay, so that's indeed a Z2 action. So by definition, okay, so this is counterintuitive why this is a Klein bottle. And I promise you that, well, some of you haven't seen, it's hard for me to visualize Klein bottle. But we'll do similar things for the Möbius string. And then you will see that actually this type of algebraic discussion will be alongside with your intuition, the way how you make a Möbius string, for example, by simply twisting and gluing with a twist. Okay, so that will come clear. But for now, we can think of this as just a definition of a Klein bottle. Okay. So we went on a double cover, and I specified how do I identify the point, right? So, good. So is it clear? Is it clear what I mean by identification, right? So what I mean by this is that suppose I choose a point here on this in this region, right? So this is the region sigma 1, sorry, sigma 2, and sigma 1. So it has some coordinate, right? So this guy is sigma 1, and this guy is sigma 2. Sigma 2. So then, according to this identification, this point gets mapped to a point 4 pi L minus sigma 1. Right? So this, I have to go distance sigma 1 here. And then I have to add pi towards this point, right? So this is going to be an image of this point under Z2 action, right? And so in order for me to get the time model, what I have to do, I have to make this type of identifications between points in this double color region. Okay? Yes?
Why do you need that factor?
Well, which factor of 2? Right. So, no. There is a reason for that. So, what we will discover? We will discover that in doing a Z2 orbifold, we will get an unoriented surface, right? But if you ask yourself, so what this Z2 action is doing, is it clear that the area will be reduced by a factor of 2, right? Because roughly speaking, you have half as many points, right? So after Z2 action, you get an area which is smaller by a factor of 2. But so effectively, what you will be doing when you are studying unoriented surfaces of kind of half the size, you're talking about half the size of the string. So in other words, the alpha prime, you want to keep alpha primes the same for oriented and unoriented surfaces. And in order to do that, you want you want the size this loosely defined to be the same after Z2 operation. What this means, it means that I have to start with twice as larger oriented surface to get an oriented surface, which would correspond to the same alpha prime. Okay? Any more questions? No. All right. So let's see. So this is very kind of that's a little bit not clear, right? So how do I think about this? Actually, actually, there are very simple ways how you can visualize this. And the way you do this, we have to kind of find the fundamental region. Okay? So here, the properties, those guys that I was writing here. So in principle, this is the whole, you have to see, let's go back here for a second. So this is the whole sigma 1, sigma 2 plane. But what I cut out here is a fundamental region, means that if I choose any point here, it's going to be mapped to a point outside this shaded region. Okay, so it's obvious because of the identification I'm doing, right? So sigma 2 will move to sigma 2 plus 2 pi. I'm always outside of this, and sigma 1 will move out there. The only identifications I have to do are the boundaries, and that's where I was putting arrows. So the same philosophy we want to do here. So here there are these identifications, but what I want to do, I want to understand what is the fundamental region on this double column. In other words, if I make this extra Z2 identification, it should move me away from the fundamental region. And there are two ways how you can see this. So those are two ways to view a time model. So by the way, so that you know that it's not going to be completely worthless. Those of you who will go and will study D-branes and will study oriented folds, so the cross caps that we will discuss today is going to be the oriented fold plane. Okay? So you are learning how to introduce oriented fold planes. So once you read about oriented fold planes, you can go back and do it. So let's continue. So how can we, two ways how we can choose a fundamental region on this double cover. So the first way, we're going to do the following. So I have 0 here. I have 2 pi here. And so what I'm going to do, I'm just going to cut it in a minute. Okay? So this is going to be 2 pi L. Okay? And this guy is going to be 4 pi L. So, and I'm going to define my fundamental region as this shaded region here. Okay, first of all, it's clear that the fundamental region should be half of the double cover, right? And by definition, you choose any point here, and you will end up at the point in the unshaded region. So the only issues could come at the boundary. So we have to figure out exactly what are we doing with the boundaries. First of all, one of the identifications, we still have this toroidal identification. Sigma 2 is identified, sigma 2 plus 2 pi. So what this tells me that I have to identify these edges, right? Because every point here has sigma 2 equals 0, I have to identify up here. Okay, and so another type of toroidal identification I have to do, I have to identify those points with those. Okay? So that's just a toroidal identification. So those are the first two identifications there. And now I have to look at these more complicated ones. How does this more complicated ones act on this region? And again, the only action that could happen is the action on the boundary, right? Because any point inside will be mapped to the point outside the fundamental region. Okay, so let me choose. I'm just going to consider. So let's consider. So I have sigma 1 and sigma 2, and I'm going to consider a particular sigma 1 and sigma 2, which is 0, comma sigma 2. Right. So in other words, I'm looking at the points along this boundary segment A. Right. So this is boundary segment A. So what happens with these points, right? So first of all, I can do a toroidal identification, right? So I can move this point to 4 pi L and do nothing with sigma 2. So is this clear? And then I can do a Klein-Bottle identification, right? So what does a Klein-Bottle identification? So I'm going to call this toroidal identification. So those are my toroidal identifications, and this is my Klein-Bottle identification. So here I acted with a toroidal identification. Now I act with a Klein-Bottle identification. It tells me take 4 pi L and subtract sigma 1. Take a second coordinate, which is sigma 2, and add 3 pi. Okay?
And why our sigma 2 doesn't change?
Sorry? Right, because there are two toroidal identifications, right? So one that acts on sigma, the other one that acts, one that acts on sigma 1, the other one acts on sigma 2. So this is, I think, will be extra in, this is 1 and 2. So what I did here, I acted with T1, okay? Now you can see that what I get at the end, 0, sigma 2 plus pi. So what you are finding now, you are finding that all the points along this segment A are identified, sigma 2, they identified sigma 2, 0, sigma 2 plus pi, right? So a sigma 2 is a circle, and so what I'm doing here, I'm identifying an opposite point on a circle. Right? So I'm gluing, it's hard to visualize exactly, at least for me, how you think of it. But then, so you have a circle and you identify the opposite points. So that's what the Klein-Bottle identification is doing. And this is, so this operation is known as a crosscut. Okay. this is our cross-cap. So what we are finding that this A segment is not just a simple boundary, but it's a cross-cap. Okay. So, it turns out that the Klein bottle has another cross-cap, and another cross-cap, not a surprise, will be right here. So let's see that that thing is another cross-cap. So now I'm going to look at the segment B. Right? So this is the boundary segment B. And so for this boundary segment B, I have sigma 1, sigma 2, which is 2 pi L, 2 pi L, and sigma 2, right? And so what I can do, I can just add directly with the Klein bottle identification on this. So what I would have, 4 pi L minus 2 pi L, sigma 2 plus pi. So in other words, every point on this on the segment B has exactly the same type of identification as on the segment A. Right? So it's identified 2 pi L sigma 2 plus pi. Right? So again, what we're doing, we are identifying opposite points on the circle. So that's another cross-cap. So now, I'm not going to go through that, but you can play this game. As you can see, it's very simple. And you can see that there is nothing funny happens along this segment. Okay. So how can we think about a Klein bottle? Well, it's very clear. So what I can do, I can glue together along those two edges, C and D. So that's exactly the same type of gluing I have to do in order to make a cylinder. And then I would make a torus if I would identify those two lines, but I don't. What I do, at the end of this torus, I put this cross-cap. So my Klein bottle is a cylinder in which I end the cylinder with a cross-cap. Okay? So what we are concluding is that the Klein bottle is a cylinder plus 2 cross-caps. Actually, this picture is very useful because exactly in this picture you will see you will be in this kind of way of defining a fundamental domain when you talk about propagation of, say, a one-loop diagram of all constraints between two orientable planes. So this is your cross-cap are going to be orientable planes, and then you have a cylinder, which is a one-loop diagram involving all constraints. Okay? So is this picture of Klein bottle clear? Oh. Sorry?
That's very clear.
Okay, good. So,
just repeat the question. So, by identification of points, you mean gluing these points?
yes.
Right?
So, but I have to glue it in a very funny way, which I cannot visualize very nicely, other than saying take as a circle and identify this point. And you see that once you do that, there is no kind of boundary components left. So this is a surface which doesn't have boundaries. So that's a surface that show up in closed strings. By the way, notice that in unoriented surfaces, this Klein bottle will show up at the same order in string coupling expansion as a torus diagram, right? So for a torus diagram, the Euler character is 2 minus 2 genus, right, which is equal to 2 minus 2, which is equal to 0. So Euler character of a torus equals to 0. So this is Euler character of torus. And Euler character of a Klein bottle is 2 minus 2g and minus a cross-cap, right? So in the case of the Klein bottle, we don't have any handles. So the genus of the Klein bottle equals to 0, but the Klein bottle has 2 cross-caps. So the Euler character is 2 minus 2 equals to 0 as well. And again, that's not a surprise because kind of for each in unoriented string, for each oriented surface, there should be a counterpart of unoriented, and it comes with whatever vector of 1/2. You sum them all together. Okay. So now let's go and think about a more intuitive way of a Klein bottle. And so I said there are two ways how we can use a Klein bottle. So this is a way of thinking about Klein bottle which is computationally easier when you will end up doing various computations in each of the string. But there is another more intuitive way. And so that's that's thinking about fundamental domain in a different manner, right? So I still have the same double color, 0 to 2pi, and then I have 4pi L, right? So now what I'm going to do, and of course those guys are identified, right? So those are just our toroidal identifications. And I have to choose a fundamental domain. So one way to choose it is the way we discussed there, but there is another obvious way to choose it. If I slice it by half here, okay, so if I slice it by half here, then what I'm getting this fundamental region. And it's clear, what's going on here, that any point inside this region will be mapped to a point here, right? Because what will happen, I have to shift. So if I say this is coordinate pi, I have to shift under the Klein identification. I have to shift sigma 2 by pi unit. So I will end up here. So again, the only thing we have to understand what happens with the boundary. Okay, so what you can convince yourself that nothing happens on these boundary segments. So those boundary segments are simply glued together. Okay. So once you glue this together, what you will get something like this. So you will get, I don't know, you will get this very big fat torus, but very short one. Okay. And so then we are left with those boundary components A and B, right, in which something interesting must happen. And so normally, if I would simply identify, I will get a torus, right? So let's see what kind of identification I have to make, right? So if, in other words, so if I would make identification sigma 1 and sigma 2 goes to sigma 1, sigma 2 plus pi. If I would do this identification, then I would get torus, right? So this would lead to T2, this would lead to 2 torus multiplied by Z2. Okay? So that would be simply gluing this circle to a bottom circle. But that's not exactly what the Klein bottle identification is doing. So what Klein bottle identification is doing, so I have sigma 1 and I have sigma 2. So suppose I choose a coordinate somewhere here. Right? So this has a property that I have sigma 1, 0. So let me write it down this way. I'm looking at the point along a segment. So I have sigma 1, but sigma 2 equals to 0. And so what I'm going to do, I'm just going to make a Klein bottle identification. And so the Klein bottle identification will mean 4 pi L minus sigma 1, and then sigma 2 will go to pi. Okay? So what this tells me is that the image of this point, so if I have a distance sigma 1 here, so then this point will move a distance sigma 1 here, and it will end up at the segment D. Okay? So now it's clear exactly what kind of identification the Klein is doing. So it's identifying A and B, but it's identifying it while twisting. Okay? So in order to get the torus again, we simply glue without the twist the ends of the cylinder. And so a Klein bottle, you glue a cylinder when you make this additional twist. that's a more intuitive way. That's the way how particular I saw definition and discussion of Klein-Bottle for the first time. Okay, so in this picture, so Klein-Bottle is a cylinder glued with a twist. Okay, so if we glue it without a twist, we will get a torus, and if we glue it and we make a twist, we will get the Klein-Bottle. Is it clear? Good. Okay, so if you haven't seen Klein-Bottles before, that could be a little bit difficult. But the Möbius strip is much easier. Okay, and so let's go ahead and discuss Möbius strip. One of the reasons is because we all can visualize Möbius strip very simple. All I have to do is take a piece of paper, glue it together, right, with a twist. It's too fat piece of paper. You've seen Möbius strips. So let's do exactly the same games. Let's play the same games with the Möbius strip. Okay, so again, so what we're going to do, we're going to go on a double color, so Möbius strip is a Z2 orbifold of the cylinder. So I make my cylinder twice as large, 0 to 4 pi L, and 0 to 2 pi. Again, this is sigma 1, this guy is sigma 2. So there is only one type of identification. In the case of torus, we made two identifications. So here there is only one identification, T2, which is sigma 2 opposed to sigma 2 plus 2 pi. Right? So this is an identification that builds for us torus, that builds for us a cylinder, and I'm not making any other identification. So again, there are two ways how we can describe a fundamental domain here. Oh, sorry, I haven't told you what's the Möbius identification. So sigma 1 and sigma 2 is identified with 4 pi L minus sigma 1, sigma 2 plus pi. So it's exactly the same type of identification we do for a Klein-Bottle. And the only difference between Möbius strip and a Klein-Bottle is that there is one unidentified boundary component. Right? So it gets identified because there is additional toroidal identification in the case of Klein-Bottle. So because of this, it's pretty much obvious that we have the same choices as in the case of Klein-Bottle. So I can choose a fundamental domain in this way. So I have 2 pi L. And so my fundamental domain is this guy here. And so now I'm just doing my analysis. I'm just doing my analysis as before. So there are two segments, A and B. So A is a crosscap, right? There is no difference here as it was in the case of a Klein-Bottle. Exactly the same identification, and well, actually no. I'm slightly lying to you. What doesn't make difference is B, right? Because if I look at B, I have 2 pi L sigma 2. And if I make a Möbius identification, which is the same as a Klein-Bottle identification, I'll go to 2 pi L sigma 2 plus pi. So B is a crosscap. B is equal to a crosscap. And so remember, A, in the case of a Klein-Bottle, was a crosscap also. But how it was a crosscap, right? So remember that in case of A, so I have 0 and sigma 2. So in case of A, if I act with a Möbius transformation, so I will get back to 4 pi L and then I have sigma 2 plus pi. Okay. So, so A became a cross cap only because this guy we moved back using toroidal identification. Right? So what's happening is that every point here is mapped to a point here. But in the previous case, those two segments were identified, and that's why we get a cross cap on A. But now it's not. We're not getting back to A because we don't have this additional identification. Right? So this identification is missing. And so when I act on points on the segment A, with a Möbius transformation, I move away from the fundamental domain. So this is not any different as any interior point here. So what this tells us that as a Möbius street, how can we think about the Möbius street then? So again, I have to glue those two guys together. So that brings me to a cylinder. So I have a cylinder, and then I have to put a cross cap here. I have to put a cross cap here, but I don't put a cross cap here. Okay. So this is our Möbius street. Okay. Is that clear? So the difference between Klein-Bottle and the Möbius street is that we are missing one cross cap. So let's look at the Euler characters. Again, we expect that this diagram will occur in a perturbative expansion of string theory at the same order as a cylinder diagram. So let's check it. In order to do that, we have to compute the Euler character of surfaces. So in case of a cylinder, Euler character of a cylinder is 2 minus 2g minus e minus c, right? So in case of a cylinder, the genus is 0. I don't have any handles, but I have two boundary components. So minus 2, and I don't have any cross member. So the Euler character of a cylinder is 0. And the Euler character of a Möbius street is going to be 2 minus. So here I don't have handles as well, but I have one boundary component and I have one cross member. It's also 0. So this tells you that those two surfaces will show up at the same order in the string perturbative expansion, right? So our string perturbative expansion, again, I erased it, is organized as a summation over all compact surfaces, right? And those compact surfaces were weighted by e to the minus string coupling under Euler character. And so it's much like when you do quantum field theory and you have to collect all the Feynman diagrams that show up at the same order. The same thing you have to do here. You have to collect all the surfaces which have the same Euler character. So in the case of unoriented strings, whenever you get a cylinder, you also have to add to your computations bullshit, which is a Möbius string. Okay, so that's one way how we think. And this is kind of brings us to our definition of the cross cap, right? But we can do a slicing of a fundamental domain in a different manner, right? So now what I can do, I can slice it in this way. Here I have 0 pi, and this is 4 pi. Okay, and so this is my fundamental. Okay, so there is no toroidal identification. Those points are not identified, and so the only thing I have to look what's happening with these boundary components, and that's exactly the same as it was in the Klein-Bottle. So what is happening here? You have to identify this edge with the top edge running in the opposite direction. Right? Again, it's simple. So if I choose a point here, sigma 1, then the Klein-Bottle identification moves it up here. Okay, so this is a picture. This picture of a Möbius strip is the intuitive one. You simply take a strip of paper and you glue opposite sides with a twist. Okay. All right, guys. So any question? No. Good. So so now we go back. And talk again about scattering amplitudes and about vertex operators. So vertex operators. So I should have kept the picture and the formula that I wrote at the beginning, but and so this is S. So I'm making X, G, and then here I have insertion of vertex operators. So that's an integral over d sigma I, G sigma I. So, so we discussed so far this piece. Now we go and talk about this piece. So the fundamental principles that we used so far in constructing follicle path integral was Weyl invariance, right? So we went into lots of efforts in order to require that all this guy up here is Weyl invariant, right? Weyl invariant. So in particular, we showed that if we, honestly, for now, if we kind of do this covariant quantization, it's not exactly obvious why do we need this Weyl invariance, right? So what we're going to discuss now is precisely, our goal now is to understand why it's good to have Weyl invariance. Right? But before we go and talk in general, why Weyl invariance is good in string theory, let's see what this implies. Right? So we want not only without any insertions, we just have vacuum amplitudes in string theory. And those vacuum amplitudes are Weyl invariant if our string propagates in 26 dimensions, right? But now once we start making the insertions, we have to make sure that actually all the amplitudes are Weyl invariant. If we say that Weyl invariance is our guiding principle, right, in constructing the string theory, then if that is the case, that those insertions are Weyl invariant. Right? So otherwise, we're facing exactly the same problem, right? So if our string lives not in 26 dimensions, then the classical Weyl symmetry has an anomaly, right? But here, if it just so happens that these vertex operators are not Weyl invariant, then we also broke this stage symmetry, which we cannot. So we cannot have anomaly in symmetries. Okay? So what we're going to do now, we're going to see what kind of constraints come from the vertex operators once we require that there is Weyl invariance. So notice that what we are doing here, we're going from omega plane to z plane. So what I can do, I'm just going to look at one of a simple vertex operator. It's a vertex operator corresponding to a tachyon, right? So what I'm writing here, I'm writing a state in a single string spectrum. 0 means that it's vacuum. I'm not exciting any oscillators, but I have a vacuum. But I have a moment. And so using operator state correspondence, that we discussed a long time ago when we talked about conformal theories, we actually know what kind of operator we end up having here. So if we have a state which is just a single string vacuum carrying some momentum, then this corresponds to the operator e to the I kx, okay? There's nothing else. So this state is a scalar in space-time, which means that it cannot have any new indices, like kind of what x has. And it must have a momentum, so it must transform properly under translations of x, because that's the way how the state transforms, and so that's the same way how this operator transforms. So what this tells us that the vertex operator corresponding to a tachyon, so this is tachyon, So notice that what I have to insert, I have to insert an integral over a wall shape, right? So I have to insert an integral over d to z, right? So now I'm in the z plane, and so I went into conformal gauge because in order for me to make this map, I have to be in a conformal gauge. And so here I will have d to the I kx, right? So this is a vertex operator corresponding to the emission of a closed string state. So it must come with a closed string coupling. So I have to put this string here, a coupling. Okay, so very good. So now let's ask the following question, right? So more precisely, what I have to mean is so this is a normal ordered operator. So now I'm inserting this operator inside this path integral. So everything up to here is while invariant, right? And so what this means that in order for the scattering amplitude involving tachyon vertex to be while invariant, V naught itself must be while invariant. Right, so everything other than the vertex, we make sure it's already while invariant. And the reason we have to make sure is because we can look, if you wish, at different kinds of amplitudes. We can look at vacuum amplitudes, which doesn't have any insertions, and so that corresponds to forcing the string propagates in 26 dimensions. So now we add this tachyon vertex operator. Everything before in path integral is while invariant. So this guy in itself must be while invariant. So what does that mean, right? So we have to ask under while transformations, how does this guy transform, right? So so the conformal weights of dz. So this is an integral dz bar. So conformal dz bar. So this guy has holomorphic and anti-holomorphic weights, and holomorphic and anti-holomorphic weights is -1 and -1. Okay, so this is H, and this is H tilde under while transformation. That's how the measure, the d to z, transforms under while transformation. So what this tells me that this operator, d to the I kx, must have holomorphic and anti-holomorphic weights, +1 and +1. So if that is the case, then the integral of e to the I kx over a wall sheet, the whole vertex operator, will be while invariant. Okay, so is that clear? So some of you who returned the homework know that, well, this we also did in class, but you practice much more. How do you compute formula and, how do you compute holomorphic and anti-holomorphic weights of various operators? And we did this in class. And so in particular, we did the computation for this operator, each is an IKX. And so what we found that this operator has holomorphic and anti-holomorphic weights. So this is weights of the tachyon operator. So it's equal to alpha prime a squared over 4, alpha prime a squared over 4. Okay. This is just from our old computations when we did conformal field theory, and we asked what are the weights. Remember the way how we did this? We looked at the OPEs, right? We looked at the OPEs of flash energy tensor with this operator. We looked at a singular part. So that was H Z squared O plus 1 over Z del O for primary operator. And so this operator is each of the KX, the ones that we discussed in class, are precisely the operators which have well-defined holomorphic and anti-holomorphic weights. And it's given by this. So what we see now that we have a restriction, what are the possible momenta, right, that our tachyon vertex can carry. And the reason for that is because those guys must be equal to 1 and 1. Right? So in other words, we are finding that m squared, right, m squared is equal to minus k squared equals to minus 4 divided by alpha prime. Okay? So we are finding that, first of all, think physically what we are doing. We are studying a scattering of some states. So the only way in S matrix our states must be on shell. So we're studying the scattering of on shell states. And what we are finding now is that if one of the states is a tachyon, we are making a prediction from the while invariance what is the mass of this tachyon. Okay, so while invariance, what we reached thus far, while invariance predicts the mass of the tachyon. Okay? And that's exactly the same mass as we found, for example, in Raycom gauge. So, but now you can see how do you get the spectrum in principle of string theory in this covariant quantization. So what you do when you study the scattering, you insist that you have that your S matrix element has while invariance, and that will constrain on the momenta of various vertices. Okay, so is that clear? So this guy is a tachyon, but in order to show that, just give you another example to show that that is the case, we're going to look at the graviton, right? So now we are looking for first excited level. Right. So, for example, here, what we are thinking here, we are thinking that we scatter a graviton, right? Okay, which occurs at the first excited level. And remember that there was a level matching condition, right? Which means that if I excite a left mover, I have to excite a right mover. So in the case of the graviton, so the vertex operator for a graviton equals to, so I have del x mu. So this simply tells me that I'm exciting a left mover. Del bar of x mu. So I'm exciting a right mover. So it carries space-time indices mu and mu. It's the same space-time indices as you expect you would have to contract with the polarization of a graviton. And then your graviton has a momentum, so I still have e to the ikx, right? So whenever a state carries a momentum, it must contain this e to the ikx simply by symmetry. Okay? Right. So, so this is something. If you look back in the lecture notes, we asked how does the first exciting state of the string get mapped when we go from omega to z, and that's exactly the map. It's being mapped to this operator, right? So again, what I have to do here, I have to integrate over the low sheet, so I have d to z. And then I have to put, it's proportional to the string coupling this string as well. Actually, if you want to be more precise, and also, from space-time, to get the right space-time dimensions, it must contain a power of alpha prime. And we will not worry about the exact memorization, but the only thing I want to mention is that this S matrix, the scattering must be unitary. And so the unitarity of the S matrix that you take actually takes you this factor of 2 units. Alpha prime is there because of the X carries space-time dimensions of length, right? But this factor of 2 is not clear where it comes from, right? And I'm saying that if you impose the unitarity of the S matrix, then that factor of 2 will come out. And this is provided that I have a freedom. How do I normalize my tachyon vertex operator? So for this particular memorization of tachyon vertex operator, this is the right memorization of the vertex operator for the first excited state. Okay. Now we're going to play exactly the same game, and the game being that we want this vertex operator to be Weyl invariant, right? So again, must be Weyl invariant, which means that it must have holomorphic and anti-holomorphic weights to be equal to 1, right? So here, well, we have this operator e to the ikx. So this operator again has the same as in the case of the tachyon. Both weights alpha prime e squared over 4. But then there is additional contribution here. An additional contribution because those guys carry also holomorphic and anti-holomorphic weights. So this guy carries a weight 1, 0, and this guy carries a weight 0, 1. And so what this tells me is that whatever the weight I have here, I have to add to it. I have to compute the holomorphic weight of the whole operator, which will be 1 plus this. And so now you can solve what is the on-shell condition for our graviton, and you'll find that a mass is minus k squared must be equal to 0. So what you are finding is that in case when you excite when you scatter the first excited level of strings, then the on-shell condition for that is that those states must be massless. And that's what we've seen before several times in our discussion. Those are the states that graviton. So we are reproducing again from Weyl invariance the condition that graviton is massless. Okay? This is Weyl invariance predicts a massless graviton. So far, I think I made a pretty strong case that we do want to have Weyl invariance in our string path, in our string theory path integral, because that leads to beautiful things that we observe, right? Okay, we haven't seen graviton yet, but we all believe there will be gravitational waves. But to kind of put the final nail in the coffin of Weyl invariance, what I'm going to do, we're going to discuss how do you derive Einstein equation using Weyl invariance. Okay, And so that will be kind of the last thing that should convince everybody that the string theory must be, that there is, well, I mean, the way to formulate string theory is to require a well-shaped Weil invariant. Yes.
Why GS carbon constitute the same for tachyon and for the graviton?
Yeah, because the idea is that you know what you have here, you have the infinite silicon lab, right? And the point is, whenever we attach a lab, we attach it with a straight carbon. So the difference between graviton or tachyon is how exactly a string is being decided. But the G string comes from attaching the lab. And that's why
it's like the same picture for.
Yeah, the only thing is that, see, when you scatter a tachyon, the string does not have any internal excitation. Remember, the string has lots of oscillators. So I'm keeping all oscillators in the ground state, and I'm just giving a center of mass momentum to the string. So in the first excited level, what I'm doing, I'm taking exactly the same string, so it must be glued in the same way. I'm specifying the boundary condition of minus infinity. And so I just excite one left move and one right.
And another question, what will be the accelerator for the photon?
Yes, you have it, but not in the closed strings. So in an open string, at the first excited level, you will see a photon. And it will come up again, requiring Weil invariance, it will come up to be massless. So now the point is...
how we can say that it's actual graviton?
Right. So the way how you can say that it's graviton, because it has the same transformation properties. Okay, so for now we are doing propagation of the string in flat space-time. But, so this vertex operator, you can see it carries the space-time indices mu and mu. Those are the same space-time indices as your graviton. Now, if you take Einstein gravity and you do linearized perturbation about flat space, you will find out that there is a massless propagating degree of freedom, which is a graviton, and it carries a polarization mu. And so for now, we are finding just an analogy. We are finding a massless state with the same polarization properties as a graviton in Einstein gravity. So the same thing you will find out when you look at the open strings at the first excited level. You will find that a massless state with the polarization properties of a photon. Okay. Now, just one second. So that does not necessarily mean that those massless degrees of freedom has, in a space-time, has gauge symmetries. Right? So we have to separate. There are gauge symmetries on a ball shape, which are diffeomorphism and Weil invariance. And now what we are finding is that Weil invariance, sort of gauge symmetries in the wall shape, predict some massless degrees of freedom in space-time. And what we're going to show now that those massless degrees of freedom actually have the gauge symmetries in space-time, and those gauge symmetries correspond to Einstein gravity and U1 electromagnetism, which I'm not going to talk about open strings, but we're going to talk about.
Yeah, so for the first excited state, we have the graviton and we also have the dilaton and the antisymmetric
Yes.
part of it. So
Right.
is this really the graviton?
Right. So yeah.
So
Okay.
much
Yes.
matters.
Yes. You're absolutely right. So again, because there is at the furthest, you're absolutely right. So I was a little bit sketchy.
Okay, so this is just
So
like
you
the
have
first
to
excited state.
do an irreducible decomposition with respect to Lorentz algebra in space-time, and that will force you to actually decompose a new object into symmetric, antisymmetric, symmetric, traceless, antisymmetric, and trace. So that will. So the only difference is how do you contract that guy? The only difference is how do you contract that vertex operator with external polarization? Yes. So they will all be massless. And so, as I said, the appearance of massless degrees of freedom imply some kind of gauge invariance. And so there will be a gauge invariance associated with a symmetric part symmetric traceless path, which will be Einstein gravity. There will be additional something that probably some of you haven't seen, a generalization of a U1 gauge invariance when we look at the antisymmetric combinations there. So they will come up. Now, what I've done, I cannot come up immediately, but I don't think there is any gauge invariance associated with the dilaton. And well, one thing is that, yeah. Okay, so I'm just going to leave it as this. I don't want to make students. Okay. All right, guys. So no more questions. So what I'm promising you now is that we will go ahead and continue thinking about one invariance, and we should be able to derive Einstein equations. And so this brings us to a new topic, which is strings in space-time. So we're going to discuss, so far we discussed propagation of strings in flat space-time, and so now we ask the question, how do we generalize it when we have a single string propagating in curved space-time? So the idea will be exactly the same. We will start with a point particle, and then we'll move to a particle string. So in the case of a point particle, what we have to do, we have to take Minkowski metric, eta mu, and replace it with the general metric, g mu, function of x, right, in the space-time. And then the action for the point particle is going to be equal 1/2 an integral in tau. So here I have a frame along the wall line of a particle. So then I have g mu as a function of x, and then I have x dot mu minus m squared. Right. So what I did, I simply replaced in a point particle, I simply replaced eta mu with g mu. And so what I'm not going to do, so we showed that when we have eta mu, that corresponds to a geodesic motion in flat space-time. So here, when you solve the equation of motion, this simply corresponds. So EOM, equation of motion, is a geodesic motion. Geodesic motion in curved space-time. Okay. So that's the way how you generalize the motion of a single particle, right? And so it's very natural. It's very natural to do the same in case of a string, right? So, well, in some sense, natural and simultaneously unnatural. So I'm going to write down, and we'll talk about it. So it will be natural, unnatural, but eventually it will be natural again. So similar means that it's natural to do this extension, so we know what we have to do for point particle. Then we have to do something similar for strings, similar for particle strings. So what we have here, so this is 1/4 pi alpha prime. By the way, this thing simply means that I'm talking about the nonlinear sigma model. Okay? So that's what I'm writing, that will be the name for this. So here I have an integral over wall shift d to sigma square root of g. So this is a wall shift metric. And then I have G and E. A and B are our wall shift coordinates. And so remember that before we have del A x mu, del B x mu. And then what we did, we contracted the space-time indices with Minkowski metric in flat space. But it's natural to do exactly the same as we did for point particle, and saying that what we are doing now, we are contracting it with a metric which can depend on x. Okay, that's why it's called a nonlinear sigma model. Because now, once a metric depends on X, what is going on here is that you have a complicated interacting theory, right? So it's no longer quadratic. So on one hand, it's natural because it's kind of generalization of point particle to the case of point string, but it's also unnatural. Okay, so why is it unnatural? And the reason why it is unnatural because we just found that in a string spectrum there is a massless state that has all the properties of a graviton. And here, what I'm doing, I'm introducing by hand an external metric, right? So my string propagates in external spacetime because there is a metric, and that external metric has its own graviton. So how does a string graviton relate to this graviton? Okay, so that's unnatural thing because looks like there are several gravitons, and we don't want that in a string theory, right? So the way how we think about the string theory, it must not have anything brought from outside. So it must contain everything in itself. And so that's unnatural. So unnatural. Now, so it was natural, now unnatural. To introduce mu X for the reasons that I just explained. And I told you that now we go back and explain why it is actually natural. Okay. And then that thing is actually something that's already contained in the string theory. Good. So what we're going to do is I'm going to show you that, okay, so now we have a path integral, right? So the path integral for string propagating in curved spacetime. I have still dx dg. I have to divide by the homomorphic cross y. And then, so here I have e to the minus s sigma minus lambda chi, lambda chi. So that's kind of a natural path integral for a string propagating in curved spacetime. So path integral for string in curved spacetime. But again, this way of thinking, I just said that that's not a good way of thinking because that implies existence of some background metric. Now I'm going to explain to you that that's not quite true. So what we're going to do, we're going to think about propagation of a string in a slightly curved spacetime. What this means that the metric in spacetime is actually very slightly deviates from the Minkowski metric. So what we're going to do, it must be clear that I can go ahead and look at higher order corrections. But what we're going to assume now that our metric is approximately the Minkowski metric, right? Plus is a function of x. Right? And so what I'm going to do, I'm going to look at the linearized order. How does this thing look like? Two linear order. So this is just a path integral. I wrote the path integral, and now I'm going to write out this as sigma. What am I going to do? I'm going to substitute this metric in the nonlinear sigma model action up there, and expand to linear order in this parameter. And so what I will get e to the minus s sub p. So I will get a Polyakov action that will be kind of to zeros order when I go back to Minkowski metric. And then there will be one minus, and And so here I have 1 over 4 pi alpha pi, an integral over rho sheet e to sigma g a d function of x, del a x, del p x, and then there will be higher order corrections which are quadratic and so on. Okay, so in fact, if I want, right, so. But now you notice that what we have to linear order. This is precisely the graviton vertex, graviton string theory graviton vertex operator. Right? Vertex operator. So in fact, I can be very precise, right? So in this chi mu of x, if it's equal to minus 4 pi g string to the I kx, so S mu is just a constant polarization. So this is just a constant polarization. So if this chi mu happen to have this form, then this is nothing but a single insertion of a vertex operator. So now you can say that if you have some arbitrary function here, in fact, what I'm doing here, I'm doing a Fourier decomposition, right? I'm expanding it in Fourier modes, and the Fourier modes of eta mu are just graviton vertex operators. So to linear order a string propagating in a curved spacetime is the same as a string theory propagating in a flat spacetime with insertion of vertex operators. So in other words, you can think of the background that we talked about there is a background that's created by preparing gravitons at minus infinity, letting them scatter, and on top of the scattering process, you study whatever you want to study, right? So that would be, say, additional insertions of operators O1, O2. So here is O1, O2. So what we did, so let me reiterate again. So a string theory in curved spacetime is a Polyakov string. Okay, so more precisely, a string theory in a slightly slightly curved spacetime is a Polyakov string in a coherent background of gravitons, right? So is this clear? Okay. But once you realize that, you can go ahead and be more general, right? And so here you kind of study some scattering processes for string in a condensate of massless states. And your massless states you choose to be graviton. But there are other massless states. There is this antisymmetric in there, and then there is a dilaton. And so what this tells you that you can generalize a sigma model by including the condensate, right, or coherent states of additional massless states of the state. Right? So let me just write it down, what I said. So you can study string theory through propagation in a condensate of its own massless modes. Okay, so let me give you an analogy. So this is an analogy that's the same as in quantum field theory, right? So in quantum field theory, suppose you have a vacuum, right? And suppose you have an operator that can have any expectation value. So what you can do, you are not saying that, okay, this is related to questions about background independence in string theory and how I think is a way to think about it. So so suppose I have a 5 to the 4th field theory that has a complicated potential, right? And so now if I study perturbative with this theory, I can study perturbative with this theory around different possible condensates, right? So my field phi can say the condensates must describe the vacuum, perturbative vacuum of the theory. So they must solve whatever the equation of motion. But then I can study quantum field theory here. So this will be QFT1. Or, for example, I can study here, and it looks like that this is QFT2. But it's actually not different quantum field theory, even though the mass spectrum will be different, right? So, so the mass fluctuation here depends how curved the potential is. And it might have nothing to do with the mass spectrum, perturbative mass spectrum here. But we are not going to say that this quantum field theory is different from this one. Because all what we are doing, we are studying a quantum field theory around a condensate of, we have a single QFT, which I can write down del phi squared minus V of phi. So this is our quantum field theory. And we study perturbative realization of this quantum field theory around different consistent condensates of the field phi. So what I'm going to say is that that's exactly the same thing how you have to think about the string theory. So you have to think about string theory as by a string propagating in different space-time is kind of analogous saying that there are consistent condensates, right? And the string propagates in this consistent condensate. So here, how do we choose this consistent condensate? What's the condition? Who can tell? In the case of the quantum field theory. Oh. No. How do you choose? How do I choose which point? I mean, I cannot study quantum field theory here. Minimally, right? So what are the equations that describe me the condensate, right? Those are the equations in the case of the quantum field theory. So it's a unique quantum field theory, and it gives this condensate. So what we're going to do now, we're going to derive the equation for the condensate of the massless modes of the string, kind of their generalization of this. And that's what we will see Einstein equations. Okay? Yes?
But shouldn't, because the propagating strings in these condensates that can also emit strings and particles.
Yeah, those are
Shouldn't there be a back reaction?
No, those are non-perturbative effects, right? So it's exactly like here, I do my perturbative quantum field theory. When you write down Feynman diagrams and compute loop corrections and all that stuff, you do perturbative quantum fields. It doesn't say that you cannot go to this vacuum. All you have to do is just do tunnel, right? And then you can probe degrees of freedom sitting in the other vacuum. Exactly the same thing in strings. So there are non-perturbative effects which relates different vacuum in string theory, which are not, which just can be separated. Right?
So this kind of formulation is not like QFT curve space-time.
Well, okay, so no, I would say that the string theory in curved spacetime, the way how I think about string theory in curved spacetime is exactly that. A different curved spacetime corresponds to different condensates of the string theory. Of course, this interpretation implies that it makes sense to talk about spacetime. Okay, which means that this space is the space is not wildly curved. So there are, and that's something that we will see. We will see Einstein equations coming up kind of analogous to this, and then we will see that there will be corrections to those Einstein equations. And then the question becomes, when you talk about space-time, what do you mean? If you mean Einstein gravity, then the Einstein gravity will correspond when the corrections are not important, and that will be true if the space-time curvature is small. Okay? So in this sense, you will reproduce that Einstein gravity. And how does Weyl invariance fits into all that? Because the equations that we will derive analogous to here in the string theory will be equations when we require violent variance on the whole sheet. All right, guys, so, but let me do what I was telling. So here we looked at the condensate of gravitons, but the graviton is just one massive degree of freedom. So we can look at positive degrees of freedom. And so that gives us, if you wish, the more general nonlinear sigma model. Okay, so sigma. So this is a Polyakov stream propagating in condensate of its zero nodes. So Polyakov stream propagating. So this is going to be equal to 1 over 4 pi alpha pi, and integral m sigma square over g g a t delta x delta x g a d plus mu. Okay, and then I have plus. Okay, so I comes because I'm living in Euclidean space-time. There is on the wall shape. So if I go to Minkowski space-time, there is no I. So I have epsilon AB. Epsilon AB is graviton symmetric tensor. Then I have B mu as a function of x. And then I have del A x mu, del B x mu. Okay. And finally, I have plus alpha prime, the curvature, right? So before it was a topological quantity. So this is a Ricci scalar on the whole sheet. But it was topological when our dilaton was a constant, right? So, but now I am allowing dilaton is one of the vast degrees of freedom, so I'm allowing it to vary. And so that's a more general sigma model. By the way, now it becomes clear that the string coupling is not an additional. Remember, I was telling you a long time ago that the string coupling is not is not a new parameter, and we see this explicitly because the string coupling is just an expectation value. So what we call lambda is just an expectation value of phi. So if we say that phi is a constant, right, or some slowly varying function, so it's a leading order in derivative expansion, I can say that this is a constant, and so that's what I mean by the string coupling, right? Good. So here notice. Okay, so everything I did here is a general extension. Is pretty obvious, and I can repeat exactly the same story I did with G mu for the other two fields. But here, what I want to point out is that with introduction of this B mu, there is an additional symmetry. There is an additional. Well, first of all, once I introduce G mu, then there is a diffeomorphism invariance in space-time, right? So there is diffeomorphism invariance in space-time, kind of involving mu and mu indices, right? So x transforms as a coordinate in space-time. So those are the coordinates in the target space. So the general terminology is that here you have a nonlinear sigma model. It's a two-dimensional field theory, and this two-dimensional field theory has fields x. So these x are coordinates now in a space-time, right? So Usually when we talk about the space of fields, that's called the target space. So a target space for this nonlinear sigma model is a space-time in which the string propagates itself. And so our axes are just coordinates there, and there is a diffeomorphism invariance if I just say that the metric transforms in the right way under spatial diffeomorphism. Actually, so that's one type of asymmetry, gauge symmetry, which is just a symmetry of Einstein gravity. But then there is another symmetry. So when d mu nu goes to d mu plus del mu zeta mu minus del mu zeta mu. So you can substitute this, and you can see that the sigma model transform plus boundary terms. And there is a way to deal with this boundary term. So in case of closed strings, we don't have any boundaries, so the boundary terms are absent. And so we will have an invariance of this nonlinear sigma model under this additional gauge transformations. So what are these additional gauge transformations? So in order to explain what's going on here, so let's go back to a U1 abelian gauge series. So in this case, we have a mu, a gauge potential, and there is a gauge symmetry when a mu goes to a mu plus del mu of some gauge function, which is a scalar in this case. And then we have f mu, which is del mu a mu minus del mu a mu. And so this guy is gauge invariant. So there is a differential form way of thinking about this. So we're going to say that A is just a one form. I'm going to write it down as a mu dx mu. I got familiar with differential forms a little bit. Okay. So just for those who I'm sorry, I don't want to go into discussions of differential forms here. But anyway, so a gauge potential is a one form. The field strength F is just a two form. So that's dA, right? Okay, so what this means? This means that you differentiate del mu of a mu, and you have dx mu wedge dx mu. And so this wedge means an antisymmetric product of differentials. So there is a gauge symmetry in which this one form goes to A plus d of data, where data is a scalar. And the reason why F is gauge invariant because F goes to F plus d squared of data, and d squared is identical to 0. So this guy is equal to F. So F is gauge invariant. And so in this language, so in other words, A is a one form, and a one form leads to abelian gauge series that you are all very familiar with. And so what we are finding there, that B field with its gauge symmetry is a generalization of this phenomenon, right? So B mu, it's antisymmetric in mu, so antisymmetric. So B mu actually corresponds to a two-fold B, which is just d mu, and then I have dx mu, wedge dx mu, right? So that's a two-form representation of this antisymmetric B field. And so the symmetries that I have here is kind of a generalization of symmetry when A goes to A plus B beta. So the symmetries that I have here, B goes to D plus DV, where D is an arbitrary one plane, right? So D is mu dx mu. And so much like in the case of electromagnetism, right, the field strands had two antisymmetric indices, and it was D, it was an exterior derivative of a one form. So in this case, we can introduce a field strands, right? So this is a field strands. Field strands analogous to U1 field strands in electromagnetism. And so this guy is going to be just dV. And so again, this guy is gauge invariant because H goes to H plus D squared B under gauge transformation, but D squared always vanishes. So this guy is gauge invariant. And so here you can think of this, that this B field is kind of a generalization of a photon, except that it carries, that it is a rank 2 antisymmetric tensor instead of a photon, which is just a vector. So this is a rank 2 generalization of electromagnetism. And so the field strands here, H is actually mu rho, is a completely antisymmetric tensor in three indices, much like electromagnetic field strands is antisymmetric rank 2 tensor. So this is antisymmetric rank 3 tensor. And so there is a gauge symmetry that we're finding here on a bullshit. It's just a gauge symmetry of this rank 2 potential. All right, guys. So we discussed the Polyakov action, how it get once we introduce condensates for massless modes, it turns into a nonlinear sigma model. And so we're going to take a 10-minute break now, and after the break, we talk about wild invariance of that nonlinear sigma model.